Hey, Chan Physics, Mr. Block, and we're just going to do a couple of problems off of the pink study guide. All right, these are very similar to the ones that the white study guide in my classroom, but we're going to do these ones on the pink one, and then I'm going to switch over to the longer one that I have in my classroom because it's got the same problems. But we'll start right here. So, those of you guys who are worried about this test, we've kind of been talking about it, that this test is a little bit different because you guys have gotten used to knowing if you have a equation, put the numbers in the equation and solve for the unknown variable. But this one right here requires you to remember the definitions and remind yourself all the time. So in my class, we've been doing something to kind of keep you just remembering that. So we always say period is a time, period is a time, period is a time. We've said it 1,000 times. And every time I say it, maybe one more kid understands why I'm doing it. Because every time you write down period, which is actually the capital T, you have to remind yourself period is a time, period is a time, right? And so in this problem right here, it says determine each of the following for the diagram, and they want the period. So they want a time. And so you can't give them a measurement in millimeters. You can't give them some amplitude number, which is in millimeter. You have to give them a time. All right. And we're going to do this problem and we're going to skip to the other ones because they always ask, there's like different ways to ask for the period for different pictures. But the, the one thing that you have to remember, period is a time for one complete wave or one complete motion or one complete flapping of the wings or whatever it is. And so if we're looking for a time for one complete wave, well, I'm going to draw with my finger. One complete wave is goes up, down, and then back up. And this is where it starts to repeat itself, right? This is where the motion starts to repeat itself. And so a complete wave is from here to here, and that is 0.04 seconds. So the time for the period is 0.04, or zero point 0.4, sorry, zero point 0.4 seconds. Okay, zero point 0.4, and since it's a time, we'll give it a time. 0.4 seconds for one wave. Okay. Now, frequency is always the opposite. So we have these equations. F is equal to 1 divided by T, or T is equal to 1 divided by F. They are inverses of each other. Okay. And so what we always say is once you find the period, frequency, you just write it right away. F is equal to 1 divided by T, or equal to 1 divided by 0.4. And I think we get 2.5. Okay. And frequency is in hertz. Okay. So once we find the time, and then we find the frequency with the period, then we can find the amplitude. And amplitude is defined. Remember, we're always talking about the definitions. The farthest away it goes from equilibrium. So the string would normally be sitting on a flat, but it's been put up through a wave, and so we can do the amplitude as 5 to 10 or 5. But we always just say, don't mess with that. Just remember that amplitude is always 1/2 the high minus the low, okay? Or amplitude is equal to 1/2 10 minus 0, okay? Because that's the high is 10 and the low is 0 on this y-axis, and then we get 5. So the amplitude is 5. I think it's in millimeters right there because it's in millimeters right here, millimeters, okay? So that's the first problem that we can give you that has asking you for period, frequency, and amplitude. What else can we do? Well, we can do it with this problem way down here in the back of the pink one, the last one. Okay. Now, instead of giving you a wave, we give you some words. And so it says a moped is traveling at 20 miles per hour. The piston moves back and forth 693 times in 11 seconds. How are you going to do that? Well, you're going to remember, again, period is a time. So since the capital T means period, capital T, period is a time. So we take the time in the problem, 11 seconds, right? And we divide it by the number of waves in that time, 693. Okay, they say times. And then we get some sort of number. 11 divided by 693 gets us 0.015 seconds for one wave. Now this makes sense, right? We always ask ourselves in physics, what should you ask yourself at the end of every problem? Does it make sense? If a moped is moving very fast, that means the engine is just running through all of these cycles. It's going back and forth, back and forth. And so it should only take a small amount of time for that thing to do one wave, one time up and down, the piston going up and down and putting itself back in position. Okay. And then once we do this, when we can find the frequency is just 1 divided by t, or 1 divided by 0.015. Okay, and we get 63 hertz. Okay, there's other things. I don't want to mess anybody up. There's other ways around it. You could have just flipped 693 divided by 11 to get that. But the bottom line is, once you find the period, and you remember it's a time, to put the time on the top and the waves on the bottom, you'll get the period, and then you can always find the frequency from that number. Okay, there's a couple more of those, like we had the problem where there was a pendulum going back and forth, and they had all the times on the right hand side, and so how do you find the period? Well, how long does it take for the pendulum to go forward and then back and then get back to where it started, and then it repeats itself? So we just look for the time it takes to go from here back. That's the time, and we get it, right? So I think I've said it too many times in this video. Period is a time, period is a time, period is a time. Remember that, okay? All right. And we get to the pendulum. The pendulum is a problem that we kind of walk through very quickly. But the bottom line is, if you got a pendulum going back and forth, the only thing that's going to make that pendulum have a shorter or longer period is the length of the string, right? If you remember from Unit 2, doesn't matter what the mass is. Gravity doesn't care. Gravity will pull harder on something that's heavier and make it go at the same rate. All right, so if we change the mass on the pendulum, doesn't change, okay? If we change the amplitude, so we go from here to here, that's not going to change either, because why? Well, gravity is going to make it go faster because it's got a bit further to fall. It's got the energy. So the only thing that changes is the length. And you can just look at it right here. I got a long one, it will go a long time to go back and forth. If I got a short one, it goes back and forth very quickly, okay? So the answers to these ones, if the mass of the end is increased, no change, right? If the length of the pendulum is increased, then the period will go up, right? The period will go up because it takes longer. And the amplitude of the pendulum increased, no change, okay? All right, now we're going to go to harmonics. And so they tell you a whole bunch of stuff in here that you'll need, but let's go through it very quickly on one. So it says, what's the wavelength of one wave? So you have to remember that, look at that string. The string is usually straight. So how many waves are in this harmonic? Well, it looks like to me 1 right here, then 2 right here, and a half. So there's 2.5 waves. So if they say, what's the wavelength? Remember, the wavelength is a length. What's going on with my camera there? Very strange. Okay. The wavelength should be in meters. So you say, okay, well, they gave us 1 meter right here. So the wavelength will have to be less than a meter. And so the wavelength is 1 divided by 2.5. And whatever that is, I don't know if I have that answer here or not. I do. The wavelength is 0.4. All right, what's the speed of the wave? Well, remember, we have one equation outside of the frequency one. That is that the velocity of the wave is equal to the frequency times the wavelength. So we just found the wavelength. They told us that the frequency is 70. And so velocity is equal to 70 times 0.4. Okay, and I get 28. Okay, what's the period of the wave? Well, remember, these are our equations. F is equal to 1 over t, or t is equal to 1 over f. So if they gave us the frequency and they want the period, then t is equal to 1 divided by 70, whatever that number is, okay? What's the amplitude of the wave? Well, they told us, I think they actually told us in this thing, The wave is 2 centimeters wide, measuring from bottom to top of the picture. And so if we want to do the amplitude, amplitude is 1/2 the high minus the low, 1/2 of 2 or 1. Okay. How many nodes are in the wave? A node is where it goes, it's like not moving at all. So 1, 2, 3, 4, 5, 6 nodes. How many antinodes? There's always going to be one less. So 1, 2, 3, 4, 5 bumps. What harmonic is shown? It's the fifth harmonic. And what's the frequency of the fundamental frequency? This is the hardest thing that people are having because they don't get the equation. The equation says the frequency of any harmonic is equal to the fundamental times its number. In this instance, it's the frequency of the fifth harmonic equals the frequency of the fundamental times 5, right? If we want to know the frequency of the fifth harmonic, we take the fundamental times 5. And so they told us that it takes 70 hertz to drive this wave. So 70 is this number right here. It's the frequency of the fifth harmonic equals F times 5. So 70 equals F of times 5. And so 70 divided by 5 is 14. Okay. And what's the wave's medium? The medium is what the wave is moving through. So in sound, the medium is air. And so in this one, the wave is moving through a string. So the medium is just the string. Okay, got to go quickly here. What's the difference between transverse waves and the longitudinal waves? You guys should have that information if you've got it on my WAG or Miss Moise's WAG. Transverse waves look like this. Longitudinal waves look like this. Wavelength is from crest to crest or trough to trough or somewhere in between. The crest is the top, the trough is the bottom. In a longitudinal wave, we represent it by these little dots. These are the compressions. In the middle is the rarefactions. And the wavelength is from the middle of a compression to the middle of the other compression. Okay. All right. All right. You guys can read my answers here, but resonance is when something vibrates at its natural frequency. We saw that with the bridge. We see that with instruments. We saw that with the standing wire. Constructive means that it adds. Destructive means it destroys. And so here's two waves that when they meet will be constructively put together into one bigger wave. These two waves, right, are different at different times. They're the exact opposite. So they will destroy each other, and so they make a straight line. These are in phase. These are out of phase. Okay. All right. If you're worried about Doppler effect, here's some answers. But the bottom line is just think about it. If I'm throwing snowballs at you and running at you, you're going to get hit by the snowballs faster and faster and faster because my distance is changing, right? Same thing with sound that's coming out of my mouth. If I'm running towards you, the sound is going to keep getting closer and closer. I'm the source of that sound, so the waves will hit you faster and faster. All right. These are all really very simple. You guys can write these down. Supersonic, above 1 speed of sound, Mach 3, 3 times the sound, and a sonic boom is that pressure wave that we looked at. All right. Sorry, guys, we got 1 more minute. So here are these ideas how we go from volume to amplitude. Absorption is damping, and pitch is frequency. All right, some definitions. Here's that problem we just did. Here is the third harmonic on this one and how to do that problem again with that frequency. And then here are these harmonic ones. I'll tell you right now, this is the hardest problem, so that's why I've been rushing. This problem right here with the boats, all right, because it really asks you to think through. If a boat is up and a boat is down, right, we can picture that the wave is going up and down. And so if a boat is up and then it's down, to be one complete cycle, it has to go up, down, and then back up again. And so when they tell us that that the boats are 4 meters apart and that we time that they both go up and down, returning to the same position every 6 seconds. So when they return to it takes 6 seconds, right? And so what